All right, good morning, everyone. Sorry we're starting a little bit late. We had a computer room door issue here in Athens, but it's all figured out now. All right, so last class period, we did not meet in person. I asked you all to watch a video that I sent by email, which was basically just a lecture, so there was no coding in that video. Today, my goal is to finish this lecture and most likely get started with the coding part of it. And I do want to, before we pick up where we left off on the video, I do want to just do a quick review of what we talked about in this past lecture that was recorded. And then if you have any questions about that, we can answer them and then get back to continue progress here with this lecture. All right, so let me see here. So those watching via Zoom, are you seeing? Can somebody confirm to me if you can see the actual presentation and not the speaker mode presentation?
It's just giving us speaker mode.
Oh, you're seeing the speaker mode. Okay, let me change that here. Well, I'm not sure why it's doing that, because supposedly it should just mirror. Let me see if I can force it to mirror instead. I'm not sure if anyone has any ideas. So I'm on a Mac, and before clicking on the presentation mode, my screen is mirrored. So I'm not sure why it's not mirror once I present. Okay, I think I got it. All right, so quick review on what we talked about last class that you watched on video, and then we'll resume with today's content. Okay, so we first talk about why variable rate, basically because we have variability in the field that can stem from soil properties, like in this case here, a map of soil pH, or just crop vigor that is a function of those soil properties being variable as well. So here's just a map of green NDVI on this field where we see different crop growth patterns. And so if we have variability in this field that affects how a crop grows and the yield potential, why would we apply a fixed rate of an input, especially nitrogen? So we talked about stable nutrients and unstable nutrients. So in the case of stable nutrients, you're thinking of things like phosphorus and potassium that you can create a variable rate recommendation by taking soil samples. The gridded soil samples, knowing where they're coming from, create maps of phosphorus and potassium levels, and then apply those nutrients at variable rates. Those are more stable nutrients because they will not be lost to the system as easily as will nitrogen. So in the case of nitrogen, it is an unstable nutrient that if we apply it today and it's a sandy soil, we have a heavy rainfall right after application, we may be losing a good amount of that fertilizer that we just applied. So it's very mobile, it's unstable. It's a nutrient that I can collect soil samples, I can analyze that for soil nitrate, but it doesn't necessarily mean that whatever I collected and analyze at a given point will be there for the crop when it needs it. It can be lost to the environment. So here was just a quick idea of how much nitrogen can be lost. There are three main pathways. So the first one here being ammonia volatilization. the second being nitrate leaching, and the third one being nitrous oxide emissions. Especially here in Georgia, if you are in the southern part of the state, nitrate leaching is going to be one of the most important pathways of loss because we have sandy soils. We can have very intense rainfall events, and even just irrigation, if managed improperly, can be conducive to nitrate leaching losses. And this can really, on average, is about 16%, but it can go all the way up to about 80% of what you apply. So imagine you apply 100 pounds of nitrogen per acre today, and you may be losing that very quickly, almost all of that, depending on the conditions that follow. So it is lost in large amounts, but is also one of the most important limiting factors to yield for crops like corn and cotton. So it is necessary, but it's also very unstable. And it's also, because of that, it's also very variable in the field. So this is just a map of the economic optimum nitrogen rate. So the amount of nitrogen that would optimize profit in this field. And we see that just within that one field, this can vary from 0 pounds of nitrogen or 0 kilograms of nitrogen per hectare, all the way up to 280 kilograms of nitrogen per hectare. So it's really dynamic, and therefore it's something that is hard for us to make a prescription based on soil properties. It has to be something that is more reactive to the conditions of that growing season in that field. So we talked about the 3 variable rate components being sensor, algorithm, and variable rate equipment. On the sensing side, we talked about active sensors. In this case here, active proximal sensor that is scanning the crop as the boom is moving over the field and potentially making a recommendation on the go as well as it moves across the field. We talked about passive sensors, one of the examples here being a drone with a multispectral sensor, which I guess if we're doing research, most of you may be working with something like this. And then lastly, a passive satellite sensor that can also be used. If you think about it, the active proximal is the least scalable because it's a sensor that the grower needs to have on their equipment, and means that they will only know how much stress there is and how much nitrogen is required once they drive over that field. So it's the least scalable. The drone is in between scalability here because you don't have to have the sensor on an equipment. It can be flying on a drone. However, there are also limitations of how much area it can cover with the drone, battery issues, data processing, and all that. Satellite, on the other hand, is the most scalable option, right? So it's going to be flying over a field whether you want it or not. So we can use that data to also assess crop vigor and make recommendations. It's the most scalable, but any sensor here that is passive, meaning that it requires sunlight to work, which are the passive multispectral on the drone and also on the satellite, they're going to be prone to environmental conditions, right? Which the active will not. So there's some different trade-offs here to keep in mind. We talked about this typical response of plants to light. So normally plants would absorb most of the reflectance on the visible range, which goes from 500 to 700 nanometers. And we call those, normally we break down those in 100 nanometer increments and call them blue, green, and red. And then we have this red edge region here, which is when we switch from absorbing a lot to reflecting a lot, that we call red edge. And then we have the near infrared part of the spectrum. So normally these are some of the bands that are most commonly used in precision ag when it comes to assessing crop vigor. Something to keep in mind is that different sensors have different sensor bands. So here, just give you an example of those 3 cases where Optrix is the commercial name of the active sensor that can be mounted on a sprayer or on a boom and already apply variable rate nitrogen on the go. So it has 3 bands. We have Sequoia, which is a multispectral sensor that mounts on a drone called EB. And here we see the bands that it has. So it has a green, red edge, and infrared, and how much of the spectrum is being averaged and considered that band, right? So just because a given sensor has a given band, it does not mean it's the same across different sensors. As you can see here, for example, comparing PlanetScope, which is a satellite, with Sequoia, which goes on the drone, the near infrared amount of wavelength that's being averaged and being called infrared is very different from Sequoia to PlanetScope. So just because we give these regions of the electromagnetic spectrum names, does not mean that they mean exactly the same across different sensors. We need to be aware of that as well. So we talked here about how can we use this information to relate to crop vigor. I'm not going to go into a lot of detail here, but basically to say if we think of leaf 1, which has the most chlorophyll, leaf 20, which has the least chlorophyll, and how they look like to a sensor. So the dark green leaf here, we see that absorbs. So the reflectance is going to be reduced because it is absorbing most of that. It is absorbing in the visible range to run photosynthesis. So because it is absorbing most of that in the visible range, it is therefore reflecting very little of it. So we see that the dark green has very little reflectance on the visible, and it has very high reflectance on the near infrared compared to the yellow leaf, which has a larger reflectance on this part of the visible here, and then the relatively lower reflectance on the near infrared. So the visible is associated with pigmentation. So the more pigments, the more chlorophyll, the less reflectance because it has more pigment to absorb the light and run photosynthesis. The near infrared region is related to leaf structure and biomass. So the more biomass a crop has and the healthier that biomass is, the more we reflect on the near infrared region. So a very healthy plant reflects little on the visible and reflects a lot on the near infrared. So we combine both of these informations, these two different pieces of information of pigment concentration and also biomass into vegetation indices. So we talked about NDVI, which is one of the most common, the green normalized vegetation index, which is the same as NDVI, but uses the green band instead of the red. And then the NDRE, the normalized difference red edge, which uses the red edge instead of the red in the NDVI formula. So here the red has some issues with it, especially if you, after a certain amount of biomass and a certain concentration of chlorophyll or pigments overall, the red band saturates, which means that you can tell apart a crop that's unhealthy from healthy with NDVI, but it's harder to tell apart a crop that's healthy and very healthy with NDVI. Whereas green NDVI and NDRE compensate for that because they're not using the red band, which is the one that saturates. They're using the green and red edge, which do not saturate. So you get back that sensitivity of being able to differentiate healthy and very healthy with green NDVI and NDRE. So we did some calculations here. I'm just going to skip because it's just plugging in the numbers. So we talked about the available bands in a sensor and the vegetation indices we can calculate will depend on what bands are available in that sensor. So here, for example, we can see that we cannot calculate NDRE using PlanetScope because it does not have the red edge band. And then we started talking about algorithms. So now we have this. So remember the three components of VRN: sensor, algorithm, and variable rate equipment. So we talked about the sensor, now talking about algorithms. There are different ways of categorizing algorithms. Two of them would be if they are specific to a given vegetation index, or if they are not specific to a vegetation index. So one that is specific to vegetation index would be when it's built. So let's say you have all these trials, you're collecting NDVI data and relating that to nitrogen rate, relating that to crop vigor, and also in the end of the season to yield. So then you create this relationship between nitrogen rate, yield, and NDVI. Now you have this algorithm that may work very well for that study that you had, but if you're trying now to extrapolate this and use that regression relationship you created to predict the same thing in a different field, especially if you're using a different vegetation index, is not going to work because it was built with NDVI as the vegetation index of choice. However, if you have an algorithm that is not specific to a given vegetation index, it's probably going to be more easily generalizable to other areas, even if you're using a different sensor or different bands and vegetation indices as the ones that you used when you developed it. So we looked into this example here, which we have two algorithms here being developed that were developed by Missouri and Oklahoma and the universities there. we see here that it has this relationship between NDVI and nitrogen rate. As you increase your NDVI here, so as NDVI goes past 0.3, you apply the most nitrogen here in the case of the Missouri one. So you apply a fixed rate of I think about 100 pounds of N per acre. And then if NDVI is greater than 0.8, then it applies nothing. The Oklahoma one has this different shape here, but it's also very similar, where the more NDVI you have between a window, you're applying more nitrogen, and then you apply nothing below a given threshold and nothing above a given threshold. Basically, the concept is that if you have very low NDVI, you probably don't have too many plants there. Or even if you have plants, they may be already stressed to a point that you cannot recover anymore, so you don't apply anything. On the flip side of that, if you have a very high NDVI, you're assuming that those plants are already very healthy. They don't need as much nitrogen, so you will not be applying much there. And then in between those points is where you would work with this algorithm and relate a rate with NDVI. However, we see that depending on the algorithm that you use, you're going to have a different answer for a same level of stress or same level of NDVI. So here, I give an example of NDVI 0.6. You're recommending different amounts of nitrogen just because of the algorithm. So imagine the sensor being the same, you're getting different recommendations because you're using a different algorithm. So some issues here is with these algorithms that are specific or were developed to work specifically with a given vegetation index is what if that vegetation index is not the best choice? So if you're working with cotton, with corn, there's going to be a point in the growing season that your red band is going to saturate. So here we see that when your crop has above a leaf area index above 3, your NDVI saturates, meaning that it cannot tell apart much of a difference between leaf area index of 3 to 5, where it could have between 0 and 3. So this is what I mean by saturation, is your red band saturates. So if NDVI is not the best option and you're using an algorithm that was developed using NDVI, then you're out of luck. Also, something else that this does not account for is if you have different growth stages. So if a crop is stressed or not, it is going to increase in vegetation index over time because it is growing, right? So here we see just an example. So this was a study from Texas and a few other states where we see a lot of data was collected. And this is just so for each different trial, in this case in Texas, we see a line here of that trial of day of year on the x-axis and DVI on the y. And so if we just look at the orange line here, if I come at 180 days of the year, it's going to have a given NDVI. And if I come a little bit later, it's going to have a different NDVI. Now, is this because of nitrogen stress? It could be, but it may be not. Most likely not. It's just the crop is growing and therefore it's increasing in biomass, whether it's nitrogen stress or not. The other point that we talked about here is what if I have different varieties in my field? So let's say you're a grower that you're growing 2 varieties or 2 hybrids of 2 different types of hybrids of corn, and they look different to a sensor like here. So here is data, is a drone flight over the corn variety trials that are run by Daniel Mailhot here, UGA. And I hope you can tell on this image here that we have different looking corn that has nothing to do with nutrition. It has nothing to do with nitrogen deficiency or sufficiency. It is because they are different hybrids that look different to a sensor. So what if you have then different hybrids in your field? How do you account for that if you're trying to apply variable rate nitrogen? How do you know that the signal you're picking up is because of a nitrogen stress and not because of variety differences? Do you need a different algorithm for each variety? Has that been developed? So there's a lot of these questions to keep in mind. So one of the ways that some algorithms incorporate or address these issues is by using some type of normalization based on the field itself. So what do I mean by that? One of those ways is using, so it's Well, I guess for this to work, you have to have a couple things. One of them is to have a high nitrogen reference in your field. That is normally a part of the field, at least in research, that you would apply a higher nitrogen rate and you would know for sure that part of the field is non-nitrogen deficient. You would assume that part of the field has enough nitrogen, is not going through a nitrogen deficiency, and you use that as your reference. So then you go and sense the remaining of the field that may be receiving variable rate, and you compare both of those. So you compare the part of the field that could be receiving variable rate with the part of the field you're assuming has enough nitrogen already. And we combine both of those numbers in something that is called a sufficiency index, which is dividing the vegetation index of the field by the vegetation index of the reference. So for example, on this example here that I'm showing you the picture, if we were to come to this field and scan this part that you see here, I hope you can tell by the picture that this part, this strip that we're seeing is deficient. It's a little bit yellow in color and not as dark green. So that would be deficient. So let's say we go there and we measure NDVI and it comes back with an NDVI value of 0.35. Then we go to if you see here on the left of that strip, there's a strip of healthy corn that was the same variety, planted the same date. The only difference is that it received a higher nitrogen rate. So we go there and we scan it, and let's say that it gives an NDVI value of 0.61. Now we combine both of these numbers in again, what we call a sufficiency index, and you can see the formula right there. So we would be basically dividing the field VI, 0.35, by the reference VI, 0.61, we get this value back of 0.57. So now, by doing this, by having a reference on your field, it does not matter what sensor you're using, what vegetation index you're using. It does not matter if it was planted at different planting dates, different varieties, different management. None of that now matters. As long as the only difference between your field and your reference is nitrogen. As long as that's the only difference, then everything else gets normalized, and you really can make inference about relating what the sensor is telling you to nitrogen deficiency and making sure that is not something else, right? So let's say if I did have two different varieties in the field, I would need to have a high nitrogen reference in both parts of the field where different varieties are. So as long as you have a reference in your field that you know is not nitrogen deficient, and you have the reference for different conditions, let's say planting date so planting date would affect your stages, right? So if you have different planting dates, different varieties, different sensors you're using, as long as you have a reference in the field that represents that management, and you have a reference that is nitrogen sufficient, then you should be able to make a recommendation that is independent of anything else. I think this was probably the point where we stopped on the video that you watched from Friday. So I do want to just, take a quick break here, or not a break, but take a quick moment and allow anyone to ask any questions if you have. Go ahead, Neva. So Neva here is asking what vegetation index we're talking about here. It's really independent. As long as you're using the same vegetation index for your field and the reference, it doesn't matter. So we're going to see an algorithm in the next slide here that was actually developed with SPAD. So a SPAD meter is something that's handheld, you go and measure. But that same algorithm, because it is not specific to a vegetation index or sensor, has been used with all different types of sensors, all different types of vegetation indices, because it is generalizable. It's not specific to a given sensor or VI. So the same here, you could come here and use NDVI, green NDVI, NDRE, whatever it is, you can plug here in this approach. Yep. Yes, as well.
So these algorithm tells you the difference in like healthy plants and unhealthy plants. So does it also tells you how much nitrogen to apply based on that difference?
Yes, that's what we're going to see in the next slide. So in this case here, we're basically first scanning the crop, getting this relative difference that we put into a ratio. And then this number, the sufficiency index, is what's going to go into the algorithm. So it's not the vegetation index itself, It's the sufficiency index, which was calculated based on the vegetation index. But it's not like NDVI that goes into the algorithm. It's the sufficiency index that goes into the algorithm. So we're going to see that next. Before I move to the algorithm, any questions online? Right. I don't hear anything, so I'm going to keep moving. All right, so I want to introduce you this algorithm called Holland-Shepard's algorithm. It was developed at the University of Nebraska-Lincoln, where in Nebraska, there is a large interest in variable rate nitrogen application, especially in corn. They plant a lot of corn, which requires a lot of nitrogen. They have a lot of sandy soils in the state, and they have the most intensively irrigated area in the world, I believe. So corn, lots of nitrogen, sandy soils, irrigation, that's a perfect storm for nitrate leaching problems, drinking water issues from nitrate leaching, and so on. So they developed this algorithm there out of that type of research. And really what I want to call your attention here to this algorithm is that, so NAP, so the green term here would be your sensor recommended nitrogen rate, where everything here is in pounds per acre. If you're working in the metric system, as long as you have everything in kilograms per hectare, it works the same way. So the way that this algorithm works is it has two components. One of them is where we determine how much nitrogen you should be applying to this field as a fixed rate. The second component is the sensor information that then modulates how much nitrogen you should be applying based on the crop stress. So the first component here is what we see EONR minus nitrogen credits. So EONR is the economic optimum nitrogen rate in pounds per acre. Now, the way that this algorithm was developed, so if you think about it, if you're doing research with nitrogen in any crop, well, you probably have a study where you go apply different nitrogen rates, and then it comes to the end of the season, you harvest that field, and then you develop an equation to see what was the optimal nitrogen rate for that field. Probably going to do that in your studies if you're working with nitrogen. The issue with that is you only learn what was the optimal nitrogen rate for the field at the end of the season, when you have harvest, when you harvest and you have yield data, which is not what we want here, because we want to make this decision at V4, at V6, V12, sometime during the season where you don't have yield data yet. So the goal here, the way that this algorithm was developed, was this EONR, the economic optimal nitrogen rate. So the amount of nitrogen that you would have applied to this field to optimize economic return is a number you get from the grower, is a number you ask the grower, what has been the nitrogen rate that you apply to this field that seemed to have worked for you. So that comes basically from experience. It's not something we're trying to estimate ourselves. It's just something we're trying to get a good number from the grower. So they would say, well, I've been applying, I don't know, 250 pounds of nitrogen per acre. Okay, great. We take that number, we plug that into EONR. Then we reduce any credits, any nitrogen credits from that number. So if this is in season application, so variable rate in season, right? So if you're coming in season applying nitrogen, you would have probably applied at least some nitrogen at planting. So we come here and that would be a nitrogen credit that you would have to remove from that total EONR. If you're irrigating and you have nitrate in your irrigation water, that's a credit. If you have had a previous legume crop, either a crop or a cover crop. So let's say if you planted, I don't know, maybe soybeans or peanuts in the previous season, that's a credit that should come into this algorithm here if you're using this for corn or cotton. Or really any other credit. So if you're applying an organic amendment, like some type of litter, that would be a credit here. Anything that has nitrogen in it, you would reduce as a credit. So you determine how much the grower thinks they need, minus any credits that's already in the system. That gives you this total nitrogen that should be applied side dress or in season. Now, the second component of this algorithm, where you can see the square root of 1 minus SI divided by delta SI, is basically bringing that sensor information from the field from this season, right? So you're taking this, like let's say you took an imagery yesterday to make a recommendation today. It's very much a reactive approach where it takes into account what's happening this year. because this year might have been a totally different year from last year, right? Based on weather. So you're taking that imagery, very fresh imagery, calculating sufficiency index, plugging that number here. Notice how sufficiency index is not in DVI, is not in DRE, is not a SPED, is not any of that. All that was already accounted for when you calculated sufficiency index. So now sufficiency index, even though it was based on a given sensor information, sensor vegetation index, but now it's just sufficiency index because we normalize it. And then we divide that by delta psi, which has a default value of 0.3. And I have a slide here to show you what is delta psi in a little bit more detail. So I'll pin this for us to talk about in the next slide. Yeah.
So in a products and fields, so how do you state a high nitrogen difference? Or you just apply the first dose of the nitrogen, then choose the area that has like the most, suppose, for example, NDI or something?
Yes, that's a really great question. So Ujwal is asking, so in a commercial site, how do you have your high nitrogen reference? So when this algorithm was initially developed, they would recommend that a grower either applied a higher nitrogen rate at planting, so they would have a part of the field that they would know was not nitrogen deficient, it was nitrogen sufficient. But you know, that is sometimes growers don't like doing that. And in some parts of the world, that's may not even be possible legally. And so there is a alternative to that, which I think we're going to talk about in this presentation. And if not in the presentation, we're going to talk about in the actual coding exercise, which is to create a virtual reference. So that concept of the virtual reference is basically one where you would sense, so if you're flying and you have an image of the whole field, you would use that image to create a density plot of, let's say, if you're using NDRE as your vegetation index or NDVI, whatever it is, you create a density plot of the NDVI, let's say, and then you select a 95th quantile of that distribution, and you set that NDVI value as your reference. So that would be the virtual reference concept, which then does not require you to apply a higher nitrogen rate and create a physical nitrogen strip, nitrogen-rich strip, but you get the distribution of NDVI across the whole field and use that distribution, statistical distribution, to get the 95th quantile and set that as the reference. So we're going to do that in the exercise when we come to that. But yeah, those are very good questions. They're very important to think about when we're determining this. All right, so I just want to show you here what is the delta SI. So just to remind you, delta SI is a number that has been used. I mean, the algorithm, you can calculate it, but for the most part, people use as a default value of 0.3. So how was that determined? How does that come about? Is you have, so imagine here you have your nitrogen rate going from, on the x-axis, going from 0 to 200. And then you have your sufficiency index. So the value that you calculated dividing by a reference, right? So what the delta SI here is basically the difference between, so if you apply, in this case here, if you apply no nitrogen, and you divided the vegetation index of that plot by the reference, so the reference has a sufficiency index of 1, right? So imagine your reference was 0.65. If you divide 0.65 by itself, is going to be 1, right? So your reference here has a value of sufficiency index of 1, and then you have your different nitrogen rates. So if you apply no nitrogen, in this case here, you would be getting a sufficiency index of 0.7. And then as you increase your nitrogen rate, your sufficiency index is increasing until reaching a plateau. This distance here on the sufficiency index scale from applying no nitrogen to the level of the N optimum, which would be the nitrogen rate where you start reaching the plateau on this equation, is the delta SI. So 1 minus 0.7 equals 0.3. That's the default value of delta psi on this equation. So basically giving you an idea of how much room you have to recover if you apply no nitrogen to make it come all the way to the health or nitrogen nutrition level of your reference. That's basically what delta SI is this difference here between 0.7 and 1, which again, 0.7 coming from the zero nitrogen treatment, 1 coming from the reference value. All right, so I just want to show you here the whole workflow of how we would analyze this data. I do want you to pay attention here because we're going to be doing this in our coding exercise. So if you're interested in the workflow, general picture is going to be easier for you to get the idea. So it would come to a field, you would use one or more of the sensors we talked about. So the active proximal, the passive drone, passive satellite. You would get reflectance data on different bands. So here I'm just picturing the green, the red, and the infrared. You combine these bands into a vegetation index, whatever that would be. You then extract the vegetation index from the field, but also from the reference, and plug those numbers into the sufficiency index formula. You then plug the sufficiency index value into the algorithm that I just showed you, and that gives you a variable rate nitrogen. So we're going to be doing this, and the way that we're going to see this is really this variable rate nitrogen changing very frequently in the field. So here I'm just showing you kind of the workflow and giving you one variable rate at the end, but this is going to be done, or this variable rate is going to be changing very frequently within a given field. And you're going to see that in a moment. All right, so I have a quiz for you. I need to make it visible, and while I make that, I just want to explain to you what this is. So here's my question for you. You go to a field with a crop sensor, whatever it is, and you measure green NDVI. Over this area that is showing nitrogen deficiency symptoms. So the green NDVI value for that area is 0.5. Then you measure green NDVI over an area that has received enough nitrogen and looks healthy. So a reference vegetation index of 0.6. Assuming an economic optimal nitrogen rate of 150 pounds of nitrogen per acre, no nitrogen credits, and a delta SI of 0.3, I want you to calculate the sensor recommended N rates, the NF. And a quick tip here is you don't forget to calculate sufficiency index first. I left you here the formula. You're going to calculate that on your side. I'm going to give you here 5 minutes. While if you want to start calculating, you can go ahead and do that because the quiz is just going to be you entering the number you find on the quiz. So while you calculate this, I'm going to make the quiz available. All right, so I just made the quiz available. It's called Quiz Variable Rate Nitrogen. I'm gonna put here 4 minutes. And then make sure you submit your answer to this question on EOC. Just pull this up. All right, let me just do this very quickly. Get this out of the way. When you're ready to submit your answer on EOC, I really just want the number of NAP. So if you find this to be, let's say, 200 pounds of nitrogen per acre, you can just tell me 200. Type in the number 200 as your answer. That's going to be enough. All right, we're down to the last minute. All right. That's it with the time. It says you're already completed. Let me see. Are you looking into the variable rate N quiz? No worries. Yeah, so the name is variable rate nitrogen. All right, we're gonna have to move on. Make sure you submit here soon, because I do want to show you, I do want to get to the end of this presentation here, so we can move on. So really, first you had to calculate sufficiency index, which would have gotten you a value of 0.83. And then you just plug in the numbers. Your answer should be 112 pounds of nitrogen per acre. If you got a little bit more, a little bit less, because of rounding, that is acceptable. I was already grading some of the cases there, but somewhere between 111, 113 is probably what you should have gotten. So here we can see that the grower would come and apply 150 by default. By using sensor, we are changing that to a little bit lower. It doesn't necessarily have to be lower. It could be higher as well. But in this case here was lower than what the grower would have done. All right, so lastly, I just want to briefly talk about the variable rate equipment side of things. Right, so we talked about the three components being sensor to collect the data, an algorithm to transform the data into a decision, and now the equipment to actually apply that decision to the field. This is just a quick schematics from Dr. Velides, showing here that you're basically going to have a VRT controller in the cabin of, let's say, either a tractor or maybe on a self-propelled equipment that has GPS. In this case here, it's showing the sensor data being collected on the go. It is assessing the crop stress, plugging that into an algorithm, creating a rate that then is fed into this variable rate technology controller that is controlling the valves of this, in this case here, the valves of this equipment, by allowing a higher or lower rates to be applied in different parts of the field, perhaps even across the boom here of this applicator. And in the end, you just get this as applied map as a result of that, so you know how much was actually applied to the field based on your recommendation. So I'm just gonna very quickly go through this first because it's not my specialty on the engineering side, but also because I want to get to the next slide here to show you all of this in action, which I think is a pretty nice setup. All right, so now bringing it all together, bringing the sensing, the algorithm, and the VR equipment into a case study that I want to show you here. This is a video I'm going to start playing. I'm going to be telling you what's going on, and so please follow along, as that's going to be important for you to understand. So this here is a high clearance variable rate nitrogen applicator that has a boom, and across this boom it has active sensors. So you're seeing here the active sensors optics. So as the boom is moving across the field, the sensors are measuring, in this case here is corn at V12. So it is a very tall corn already, and that's why we need a high clearance equipment to do this. So it is sensing the crop. The information that the sensors are collecting are already being fed into that algorithm we just talked about, which is creating a rate, which is being applied. We're not seeing the rate being applied, but below this boom here, there are some nozzles that drop closer to the ground that are actually applying the nitrogen, changing on the go. So what we're seeing here on the first plot on the bottom is the red line is NDRE, which was the vegetation index being used to apply here. And the black line is the variable rate nitrogen that is being applied. So as you can see, when NDRE is high, meaning the crop is healthy, the rate being applied is lower, as you would expect. And as NDRE drops, meaning that the crop is more stressed, then the variable rate increases. So it kind of mirrors, one mirrors the other. So crop that is very healthy is receiving less nitrogen. Crop that is unhealthy is receiving more nitrogen across this strip here. Now, this was a non-farm study, so it was a long strip trial happening on a farmer's field where there were a few treatments, but I want to highlight two of them. So one of them was what you're seeing, where the nitrogen being applied in season, side dress, was the rate was being determined by the sensor itself, right? So this rate is changing. As this equipment is moving through the strip, the rate being delivered is changing according to the crop stress. Right next to this strip here was a sensor, or sorry, not a sensor, a grower treatment, which was whatever that grower was doing as part of their traditional management, which was a fixed rate. So they would come here and let's say apply 150 pounds of nitrogen per acre fixed across that strip that they manage, right? So two treatments. One was the grower management. One was the sensor-based variable rate management, which we're seeing in action right here. Now, on the graph on top, we can see yield. So this is again, this is corn. So this is in bushels of corn per acre. And the pink line here is the variable rate, the yield coming from the variable rate treatment. And the kind of bluish color line is coming from the grower yield. So the grower that applied a traditional fixed treatment right next to this strip here. What do you see there? If you're comparing the yield coming from the variable rate strip with the grower yield. Consistency? Well, in which way? So the variable rate is being more consistent, right? So the yield here is being very consistent across the length of the strip when you compare it to the grower, where the grower sometimes was getting higher yield in some points, but it was also getting very much lower yields in other places of this field, whereas the variable rate was being very consistent across this. So this is something you would expect because the variable rate is really applying how much the crop is telling us that it needs, right? Whereas the grower would perhaps apply a given rate regardless of the conditions of that year. All right, well, I'm gonna just finalize this. If you have to leave, you feel free to leave. You can catch up the last few moments here on the recording. But I just want to finish this lecture so we can get to the exercise on Wednesday. So really, in summary here, we talked about that spatial variability exists, especially affecting nitrogen nutrition, because the underlying reasons for spatial variability are there already. Plus the fact that nitrogen is very dynamic, it reacts, it is dynamic because it interacts with your management, especially with weather, and weather changes from year to year. So especially because of that, variable rate, we have this variability in the field that can be addressed partially with variable rate nitrogen management. We talked about the different VRN components, the first one being the sensor. So we talked about how sensor understands the plant signal and how different sensors are different and create and have different bands, and those bands created differently. We talked about the second component, which was the algorithm. I introduced to you 3 different algorithms. So first one being the Oklahoma and the Missouri algorithms, and then also one from Nebraska that was the Holland Shepherds that we talked more about. We discussed the concept of high nitrogen reference and the sufficiency index and how that is important to normalize and make sure that nitrogen is indeed the limiting factor in your field and is not being affected by variety or hybrid or planting date or anything like that. We then did this exercise of calculating a variable rate nitrogen by hand. And then finally, put all this together and showed you a practical example here and the consequences of applying variable rate compared to a fixed rate on both nitrogen and yield. So this is all we had for today. I'm going to open for questions here in a moment. Next class, we're going to have an exercise, a coding exercise that's going to implement all of this. And so I do ask you to already go ahead and download the material from GitHub. You can create a new project on your side. Let me just pull here to show you. So you can create a new project on your main folder called 13 Imagery VRN. And then, of course, inside of that, you already know this. You should create the code data and output folders, create an RStudio project at that level, and then move the, so there's going to be one script that I want you to move into code that's on GitHub. There's going to be 3 data sets I want you to move as well. So one of them is called NDRE post, NDRE pre, and a plots.geojson. So please make sure you have all this done before next class, as I'm going to assume you have this already finalized, and we're going to start from that point. All right, I'm going to open for questions if anyone has them. Any questions? Yes.
You also have said like where you incorporate like the soil data.
Yes, so let me just rephrase that. So, or repeat that. Lisa is asking if we have studies where we incorporate like the soil EC or other properties. We do. So in our research studies, so especially when we're going on farm, and one, and that's a really great point, Lisa, and I want to show you here something. So on this slide here, where we saw this in action, let me just kind of like show you this at the end again. Oh, okay, it didn't work. Well, I guess what I was trying to show you was this map here, the yield again. So one question that we've had from the growers, from other researchers is, okay, variable rate is making it more consistent, but it's not capitalizing on when the grower was highest, right? So how can we make sure that the variable rate is not yielding, so it's yielding more than the grower when the grower is yielding less, but it's also yielding maybe as much as the grower when the grower is yielding more. So that comes down to the way that this study was conducted, which was using just one reference value, basically assuming one reference value for the whole field. What we could do, and what we do in our research, we're doing that here in Georgia, is to use soil EC, elevation, terrain properties, just like we did in class, to create zones first, and then correlate those zones with yield, understand what zones are driving yield more or less. And then when we so we create zones based on both yield and soil EC, terrain, and so on. And then when it comes time for doing this in season, so creating a variable rate map, we extract a reference value for each one of the zones instead of using one reference value for the whole field, which was what was done on this field, on this study. So this study used one reference value for the whole field. We're using reference values specific to each one of the zones, which may have different yield potentials. So yeah, so we do use those other layers to also inform here how much should be applied in the way of getting a zone-specific reference value. Yeah. Any other questions? All right, I know we're almost 10 minutes after the time, so I'm gonna stop here, but yeah, we're gonna be implementing this on Wednesday. I think it's gonna be a really cool exercise. So I'll see you all on Wednesday, and let me know if you have any questions by email.
Hey, quick question.
Yes.
That the infield applicator, is that kind of like a prototype or is there actual, I guess, like production rigs out with that?
No, so that is an actual commercially available equipment. It's from so the brand of the equipment is called Hagi. So it's a high clearance Hagi applicator with mounted with the sensors, and those sensors are also commercially available. The Optrix, the ones that we're seeing there, are also available.
Or
Yeah, awesome. Any other last burning questions? Okay, I guess not. So I'll see you all on Wednesday. Thanks, everyone.